So in this special topics lecture, let's discuss the relationship between symmetries and conservation laws, and then do an application to get the exact redshift formula in a static metric. So we've seen a little bit of this before when we were studying the motion in the Schwarzschild metric. We were interested in finding conserved quantities, and we found, in fact, that the momentum of a particle in the vicinity of the star satisfied a simple expression of the fact that it travels on a geodesic. If we looked at the geodesic for covariant component of its momentum, it read like this. In that case, the appropriate Christoffel symbol reduced down to just the gradient of a component of the metric, and the direction of the naive gradient was just in the same direction as the covariant momentum of interest. So we come up with conservation laws. For example, if G gamma beta is independent of time, then when mu is equal to 0, this vanishes, okay? And the quantity has a 0 derivative. P mu has a 0 derivative for mu equals 0, so it's a conserved quantity. We found that for the energy-like variable, and we found that also for the angular momentum-like variable, where mu became the angle phi. So remember this derivation, and it led us to the conservation laws of interest. It was true for the covariant components of the momentum, not the contravariant ones that we usually deal with. So we like to codify some of these relationships. See, we have a symmetry, okay? The absence of G depending upon time and depending upon phi. We had a static problem, okay? And it had spherical symmetry, okay? So the metric inherited those simplicities. It expressed the symmetry by not being dependent on T or phi, and so that led to conservation laws. Now you've seen in your mechanics course similar phenomena, similar ideas, and when you do field theory, you'll find them in a multitude of applications. So I'll leave some of our discussion to later events in your education, and I'll just be satisfied with that. But I do want to introduce some of the terminology that comes up in general relativity. In curved space-time, there's a general way of looking at these conservation laws, and it uses the work of a mathematician called Killing, and we refer to the directions in space-time for which there's a conservation law by Killing vectors. So here it is. If we focus on energy conservation, we know that the velocity for mu equals 0 is picked out as being special. Okay. In this case, over here we saw that u sub mu for mu equals 0 was conserved. We want to pick out that component in a general way. So in the case of the Schwarzschild coordinate system, for example, I might just define a vector k mu, which is 1, 0, 0, 0, 1, 0. So it picks out the mu equals 0 direction. Okay, and that's sort of handy because then, for example, I can consider the contraction of k with p. Okay, so mu is upper here, lower here. Okay, k only has a component in the 0th component in the writing it in the, let's say, the Schwarzschild coordinate system. So it picks out mu in the 0th direction, and that's a conserved quantity. Okay, okay. So then we learn that we can calculate that conserved quantity by doing a contraction of two 4 vectors. So I can imagine evaluating that dot product in any frame of interest, okay, to make it calculation easy and universal. And so I learned that this character here is conserved in this situation, okay, in this particular situation here. And so S, the contraction, is a constant. And I pulled out the factor of the rest mass here, just to write it in terms of basic coordinates. Okay, okay. And so I can write it that way. If I lower the index on k, okay, then it's related to the k direction that I introduce in contravariant notation by a g0 mu. That brings down a g00, and for the Schwarzschild case, that's we remember that. That's 1 minus the Schwarzschild radius divided by r. Okay, so there you have it. There's a conserved quantity. I can write it in terms of the g00, okay, and dx naught d tau. That's dt d tau up to a factor of c. And we've seen that combination a great many times in our discussion of Schwarzschild orbital dynamics. We used this earlier. I'm not going to do anything new here. I'm just going to codify it. Okay. Now, in many of my applications, I'm going to want to know additional things. For example, as we discussed in special relativity, we might have an observer, which is moving about in Minkowski space in some arbitrary fashion. I might ask the question, well, what does this observer observe? For example, if it runs into a particle of momentum p, what's the energy of the particle of momentum p that the observer measures? Well, to get that, you just take the product of the velocity of the observer dotted into the momentum of the particle that's being observed. That gives you the answer. And the way you understand that is you go to the observer's rest frame. In the rest frame, its velocity is c in the time direction, 0 in the spatial directions. And so I can evaluate this inner product in any frame I want to. I choose to do it in the observer's rest frame. That's where I'll have a physical interpretation of the result. If mu is c0, then the dot product brings me just p0, just the energy. Okay, so you see I can calculate that component of the energy in an invariant fashion. And boy, is that helpful, right? I don't explicitly have to boost into the frame in which the particle is at rest. I can just calculate the scalar product, and I can do that in any frame I want to. And you've seen when we did collisions and applications in special relativity how handy it was to use relativistic invariance. Okay. So for example, in Schwarzschild coordinates, we might take the observer at rest at a particular R value, for example, and I can calculate what that observer measures for the energy of a particular particle that's whizzing by. I just calculate this inner product. So I write it down in my Schwarzschild environment. I have a very non-trivial g mu nu, and I write that down here. And so there you go. Now, if my observer is at a fixed r value in Schwarzschild coordinates, okay, then the only component alpha here is alpha equals 0. So only g equal for alpha equals 0 contributes to the big sum. Okay, the Schwarzschild metric is diagonal, so alpha and beta are 0, and I come down to this. But you see, that's the kind of thing which I just calculated. Here's g00, here's dt d tau. Well, that's just my invariant S that we just had when we were thinking about killing vectors. So I can write the energy of the particle in terms of the conserved quantity S in this way. You see, this combination g naught naught and dt d tau making up S, which we decided was conserved in this situation. So E just varies like u naught, okay, which I've written down here, and u naught varies like 1 over the square root of g naught naught. Okay, so that's all that there is. That's all that there is there. How come u0 varies like 1 over the square root of g naught naught? Well, u, for example, is a properly normalized velocity vector. Okay, so u dot u is equal to c squared. This is a calculation we've done before many times. Okay, write out u dot u in the Schwarzschild coordinates for the case where u only has a component in time direction. So u dot u becomes g00 u naught, and all of that's equal to c squared. Okay, so you solve for u naught, you get that it's 1 over the square root of g00 up to a factor of c. Okay, and g00 we recall from the previous sheet, and taking the square root is just this. Okay, and so we understand that the energy of the particle goes like g naught naught, that's this stuff here, to the minus 1/2. I'm illustrating this stuff for the Schwarzschild metric, but any time independent metric, which is diagonal, okay, works as well. And so I have a more general perspective on the problem. In summary, we see that E of R goes like G00 R to the minus 1/2, which goes in the Schwarzschild case like this. Okay, so then in my application, I can do the application. I can imagine a photon being emitted at one position and being absorbed at another position, okay? And then use the fact that its energy is h bar omega, okay? And so I see that that the ratio of the energies goes like the square root of the inverse ratio of the g naught naughts. That's what we just learned, okay? So I have a photon which is observed by a stationary observer at one position, okay? It gets its energy, okay? And then that photon ends up at another position, R2, when an observer at rest measures its energy. And I know that the ratio of those energies therefore goes like the square root of g naught naught flipped over. Okay, why flipped over? Because we had that g00 to the minus 1/2 in the previous case. And so there you go. Okay, and so there's the derivation of the exact redshift in the case of a static metric. Long ago we applied this to the weak field case, and there's the answer again, because I just take this quantity and I expand it in the case where gm over c squared r squared much less than 1, and so I can tell it expand it away and get that omega 2 divided by omega 1 is approximately 1 plus 1 over c squared, the difference of the potentials, the Newtonian potentials between the 2 points. Right? So we're good at these sorts of approximations and these weak field cases. But what I wanted to do was to get it in a more general form in terms of just Z0, G00 zeros, and then apply it to many situations. And so that's what we wanted to do. So we've seen a little nice illustration, okay, of symmetries and conservation laws, and then we applied it to this case and saw how easy it made some of our calculations, and that's really the message that we want to take a look at here. Okay, so that's all I wanted to say in that special topic, and we'll move on to a special topic in special relativity next time.